Hello and welcome to our online lecture series Radar in Action. My name is Jens Fieger. I'm glad you're all joining us again. I hope you have a calculator and a pencil ready because today is going to be challenging. My colleague Simon Wagner will show today how to identify scattering in ISAR images. So radar images of objects generated by the inverse synthetic aperture radar method. This then helps with target classification. But how does that work exactly? That's what my colleague Simon Wagner is presenting now. Go ahead.
Yeah, thank you very much, Jens. And welcome everybody to my presentation with the topic scattering identification in ISAR images via sparse decomposition. The presentation is separated into mainly three parts. Actually, the first two are a bit theoretic. It's the sparse decomposition framework and the ISAR imaging and the waveguide model that will be used later. And as we can already see on the right side here, today we will have a specific look at jet engines. That's the idea behind this framework that I present today, that we can identify jet engines in ISAR images. Then we come to the results and to the conclusions. But I start with a short introduction. As Jens already mentioned, this topic is related to target recognition, so we need to identify targets that fly around. And unfortunately, you will find some examples in the past where this did not work, that civil airliners was also accidentally shot down. This, unfortunately, there are quite drastic examples where this was not working properly. And one point of these target recognition systems is that most of these systems use a list of potential targets. So they are, for example, trained neural networks that want to identify a specific number of targets or specific classes. They are trained on, for example, 10 different targets and can re-identify these 10 classes. And this work here is kind of in the middle between the ISAR imaging and the actual classifier. So the idea is to identify these jet engines as a first feature, the location, the number of jet engines, and then to create a potential list of targets so that we know we expect these aircrafts maybe in this area, that we know this can be a civil airliner with 2 engines at the tail. That's actually the example that we see here. So we see here an aircraft, and that's the ISAR image. And at the position of the jet engines, you will find them here in the image, you can see this ponytail structure behind the jet engine. This is the effect that we will use later in the waveguide model or this is the result of the waveguide model, that we have these so-called range extended returns in the image. And yeah, that's the idea of the model that will be presented later, but I start now with the sparse decomposition framework in general, which is used to separate different scattering centers. First, short definitions of the elements that are used here. We use a signal X, a complex signal actually, so we use the raw data of the radar later. And we have a matrix phi that we call dictionary and a coefficient vector alpha. This is an overcomplete system, means that the dimension of alpha is much higher than the dimension of X. So we have an underdetermined system of equations if we want to represent this linearly. And this is the regular case that we have this so-called overcomplete dictionaries. If the dimension of alpha and X are the same, it's actually, and the dictionary is full rank, that is actually a condition that must be fulfilled, that would be a basis. But we have this overcomplete dictionaries that we have more so-called atoms, means more columns in this matrix than rows. And we normally don't have an exact sparse decomposition. We normally use a so-called sparse approximation. That's what's shown here. So we have we allow a certain difference between the actual signal X that we measure and our approximation. Okay, now we come to before we come to the actual algorithm or the problem, some more point. There's actually the LP norm that is used in the framework. It's a common mathematical formula, let's say. It's defined between 1 and infinity. For infinity, we get a maximum norm. But we can also, nobody can stop us to just put there a number smaller than 1. Then we get something that is not a norm anymore, and we can actually see what happens if we use, for example, 0.5 here for p. You see, these are unit circles in different norms. So this is the one that we know, the Euclidean norm, the common norm, that a circle is actually a circle. If we use the L1 norm, this becomes square in this direction. Maximum norm becomes a square like this. And if we go below 1, we get this. And actually the so-called L0 norm, which is not a norm, gives us the number of non-zero elements. And this is actually the term that we want to minimize. So we want to have the smallest number of coefficients to approximate our problem. A different way to formalize this is this, using this Lagrangian multiplier method. Or actually this is NP hard, so we can't solve it, but we can solve the L1 problem. So we put here not the L0 norm, but the L1 norm, then we can solve this problem. This is the convex relaxation of the problem. Or in this case, we can also use this formulation with the L1 norm in the penalty term. And we will have a look at these two formulas here on the right side, now on the next slide a bit more. First, I will show you something that's called hard and soft thresholding. The soft thresholding is also known as shrinkage, which we can see here actually in this curve. So the hard thresholding is just that we remove everything below a certain, or the absolute value below a certain, below a certain value, everything is set to 0. In the shrinkage operator, we also set everything below the threshold to 0, but a magnitude larger than this, we subtract the threshold. Then we get this curve. So there's not this certain jump in here, this certain raise. So we start here at 0 and then we go linearly up in both cases. Okay, so why do we need this here? Actually, we can define a similar problem as we've seen on the slide before, but now it's just in data approximation term. So we have our vector alpha that is approximated by this alpha with this tilde here. So, but in this case, our phi is a matrix, a basis. So we can just formulate this term here. So we can just calculate the inverse and calculate this. And then if we want to minimize the L1 and the L0 terms from the slide before, so we put here p to 0 or p to 1, then we actually get these two terms for the solution. And these are exactly the terms of the hard and soft thresholding. So this basic elements of hard and soft thresholding give us a solution for this problem. And this is what used actually in the so-called iterative thresholding algorithms for sparse approximation. I don't want to go into the detail actually of this algorithm. I'm going now to the algorithm that I actually use that uses this iterative thresholding as a step in there. The assumption from my algorithm that I use here is that we can model our signal as a sum of k independent components, what we see here. So our signal x is made of several x signals actually, up to capital K here. So we have k components. And each of these components possesses an own sparse representation in a certain subdictionary. So our matrix is now divided into certain blocks, and each of these blocks represents one component in our signal. How these components look, we will actually see on one of the next slides. So this is the assumption, and then what we have to do, we have to optimize each of these terms independently from the others. So in the end, we should approximate all at the same time, which is quite hard, and there's something called block coordinate relaxation. So we fix all components but one. This means that we only optimize one component in each iteration step. We fix it, then we use another one, fix all components but the one that we just optimize, and then we go on and on like this with all the components until we have our solution, until it's converged. I will show you a quick example actually in this video here. So we have an image processing example. So we have a test scene made here of circles, squares, dots, crosses, and lines. And we want to decompose this image into, oops, sorry. Okay, I think I have to remove this one. Now it starts. Okay, now turn this on again. now we want to decompose this into the different components. This is the residual, so this is the input to our current iteration. And we can see if we have a dictionary made of squares, lines, crosses, circles, and so on, we can decompose our image into these different kind of scattering or different kind of, in this case, shapes. It's just image processing here at the moment. Now, when we come to the end, we see that our smallest threshold actually is below the noise level. So especially here with the dots, we go into the noise level and we end up with a quite noisy image in the end. With the larger scattering or with the larger shapes, this doesn't happen because we cover a lot of energy actually with one scattering, with one example. And this means we have a high averaging effect that reduces the noise in these terms here, if you calculate the correlation of this. So this was just the idea, more or less, of the algorithm. And now we come to the model that is used in the later application of ISAR images. As I said, it will be jet engines, and I will actually show you an example for waveguide scattering. But first, just as an, let's say, reminder, this is one of the basic formulas of ISAR imaging actually. This is the definition of ISAR imaging, you can say. We have a certain object that can be described by a function A. This is the scattering distribution. And our signal that we receive is given by this 2D Fourier transform in polar coordinates. If we do this kx, ky substitution with this cosinus and sinus terms, we can write it like this, as a 2D Fourier transform. This is so-called polar reformatting. So our signal that we receive is given by the Fourier transform of the scattering distribution. That means that we can just use the inverse Fourier transform to calculate our image. The point is that our signal, relies on the so-called weak isotropic scattering centers. That means that the scattering centers don't change the waveform in the end. They are frequency independent and they are, in all directions, they have the same echo. This is not true for some scattering centers, and jet engines is one example of these. There are actually two effects that happens. It's the first one that is not used actually in this work, but I mention it here because it's quite known. It's a so-called jet engine modulation. That means that the blades of the engine, they rotate very fast and they produce a Doppler spread. And this Doppler spread is then seen in the image later as so-called jam lines. So we have some bright streaks in the end, quite from left to right. If you do it Doppler from left to right in the image, in our resulting image. This is not used here. I only use here the cavity of the intake structure. So the first part of the engine that we see here. So the wave that's coming inside, it goes into the engine. That's this one. And then it goes to the fan actually of the engine. It gets reflected there. It's coming out again. That's a quite common model actually in electromagnetic modulations for jet engines. And the most important part for waveguides is that if we want to transmit a signal in a waveguide, we need to know that the field inside this waveguide can only take certain shapes. It must fit into the waveguide in the end. That we have all zeros along the borders, along the boundaries of the waveguide. And this defines so-called modes. So one mode is a certain shape of the electromagnetic field inside. And if we have certain so-called propagating modes, our signal will also propagate as the sum of all these modes. And this gives us the so-called waveguide dispersion. That means that we have a non-linear group velocity that is shown here for an example that is not realistic for our case. It's just the one that I also use on the next slide. So we see here that we have a cutoff frequency. So it means cutoff means that we have no propagation below this frequency. And then theoretically we have a standing wave at this cutoff, and then we go more and more to the normal velocity of light in this case. Here it's normalized to 1 meter per second. So as I said, it's not a realistic example. It's just to produce very friendly numerical values. This is shown here as an example of group velocity, and what this means for our signal is that our waveform is spread in time, because a part of our waveform is traveling slower than the other one, and that's now here shown as a time frequency transformation. So we have here an LFM, or also known as chirp signal, that we have a linear frequency ramp going from, in this case, 100 to 900 Hertz. As I said, it's not realistic. And then if we use the mode from the slide before, we see here this cutoff effect at 200. We can see that theoretically the standing wave will produce an infinite response in the end over the time. It's going down and down. The echo, the amplitude is going down over time. But it allows actually that the low frequencies from the beginning are passed by the high frequencies. That means that our input chirp is changed to this shape. And if we have several modes, we have the same effect. We have, in the end, several output signals from the different modes, because each mode has a different velocity, and then we have this output signal. This is an extreme case, just to visualize the effect. But if we use a matched filter in our processing, we will get a response for each chirp that we receive, or for each signal that we receive. And if we have several output signals, we also get several responses from our matched filter, and this is what we see as these range extended returns. That's the basic idea of this model. And to bring this into the ISAR equation, we use an corrective term in the end that we can see here. So we have our, in this case it's 1D, so we have only this, there's no kx and ky, there's only k at a certain range, and it's weighted by different, by the modes in the end. The magnitude of the modes, and then we have this waveguide, wave number, this kwg, of all the modes, propagating to the end of the waveguide and back. L is the length of the waveguide. In this example here that I show, the amplitudes are equally distributed, since it was shown to be empirically better, because these modes, the theoretical ones, are for a perfect waveguide, and a jet engine is far away from being a perfect waveguide. I mean, there's the air bypass, there's screws, everything. This will, also produce again all propagating modes, and actually also the so-called evanescent modes, but that's something different. We only take the propagating modes here. So what we do now for our signal, for our model, we use this corrective term, add it at the position of the jet engine, where we also have a point scatterer from the opening rim, and then we have the propagation to the fan, and then we get the first reflection. This is what we see now in this 1D profile. So our sink is now changed to this one, and if we correct this also in 2D, we put in the end the same term, but now only in the range direction. At the sink function in the end in the cross range domain, we get this. So this is our 2D basis, or atom in the end of our dictionary. So this is the model that we use in the sparse decomposition framework in our matrix phi. And that was now more or less the theoretical part. Now we come to the results, and I start with a small simulation that I made up. I just created an aircraft shape that has this waveguide scattering here at the position of the engines, and this is the resulting image. As you can see, the amplitude of these range extended returns is below the ones of the standard scattering centers. So I also created these separately. So this is my reference data. So the ideal output of my decomposition, the simulation, will be exactly these two images. And I will use the mean square error of my output related to these two images. Okay. Now, I mean, you can produce there with many possible SNRs, for example, and everything. So either this one here with a 30-degree aspect angles and 2 dB SNR after integration to have some sort of realistic data. And now we can see the decomposition process, as we have seen before with the crosses and the circles. And now we can see that this point, like scattering centers, produces again our the shape of the aircraft. And here we have the output of the jet engines actually, and there we can also see that we see all the engines, but also, for example, here at the tail we have some false alarm. There was a structure quite similar to this range extended returns. That's, I guess, this one here, just the very end. So we have like a downrange direction collection of scattering centers. This created some confusion in this case, but it's working. So we detected our engines in this simulation. So now we actually have a look already at the real data. That was measured with the TIRA system here from FHR. We can see here 4 examples. I'm sorry for the different color bar in the end, the different scaling. But this is from the same measurement, the same aircraft. And you can see that the aspect angle is increasing. Actually, this is the smallest one. You have this, and then this. And that's the image from the beginning, where we see this, the structure behind the engine, and we can also see it here, here, and here. Now we have a detailed look at the first image, and I should mention that I needed some heuristic because I didn't know the precise parameters of the engine. I only know optical images from the aircraft, but I don't know the exact size of the engine. So I have to estimate it a bit, and I used some heuristic to match it in the end. So let's say the first iteration of the algorithm didn't include a greedy step to find the maximum correlation between different parameters. So for the first image, I found these parameters. That was an opening of roughly 39 centimeters and 67.5 centimeters length. These are the parameters of the thresholding algorithms. So we have a minimal threshold of 20 times the estimated noise variance. That's the stopping criteria. So after 10 iterations, we see these 2 scattering centers from at the nose and here, and already 1 of the engines. And then we go on. You can see here this and this. So this was the first 200 iterations, and completed 400. And we already see that we have no false alarms, and we already have some strong, the main scattering centers, and also the engines. And at the final result, we can see here that we have these engine scatterings separated from the point scatterers. This is the residual that looks still like there's most of the energy inside, because we can still clearly see the shape. But if we plot actually the image energy of the residual, we see that these 2 images cover already almost 60% of the full energy of the signal. This is what we see here in this curve. These dashed lines are the lines from the images that we have seen on the slide before. And at the end, of course, the images. And now we will have a look at the other 3 images, the remaining ones. And there we can see that it's also possible to separate the scattering centers, the point scatterers, from the jet engine, and vice versa, of course. But the parameters, they vary a bit. So before we had this 39 centimeters opening. That's actually the same that we have at example 3. Example 2, the best result I got was this 42 centimeters, or this result here. As I said, it was just the first iteration. And the fourth one was more different, but also the aspect angle changed a lot from this one to this one. That's reduced to 30 centimeters, and the length is now also let's say the parameter that gave the best results is now reduced to 47 centimeters. Okay, these are more or less the results. Now I come to the conclusion, to the end. So first of all, I want to mention that I would say the results are promising, because the decomposition was possible, and it was applied in the complex raw data domain of real measured ISAR images. And simulation and real images showed comparable results. So that's always quite good, because if you have working simulations, but the real data is lacking a lot in the performance, then it's normally a problem. But here it was working quite well. But yeah, the major problem, that's what's the point to improve, of course, is of course the model itself. As we have seen, the parameters differ a bit from image to image, and yeah, that's something for the ongoing work, that we maybe add more parameters to the model and maybe also include the aspect angle dependency somehow. As I've shown, when the aspect angle changed a lot, it was, the change in the parameters was quite big. And another option would be, for example, this jet engine modulation, that this can be included. So there are many open points to continue, but this is the summary and conclusion of my presentation for now. So thank you very much. If you have any questions, I will answer them right now, or if you have some follow-on questions, you can always send me an email. Thank you very much. And now, Jens, I guess again.
Yes, thank you for your presentation. Well, I as a layman had a hard time following, but I hope there are many experts among you who are able to follow. There are definitely a few questions already as well. So the first question is, what is the resolution of the radar?
Yeah, thank you very much. In this case, it was measured with 800 megahertz bandwidth. So that gives us a bit more than 20 centimeter resolution. I think after processing it's 25 with the window and everything that's applied. So in the end it's roughly 25 centimeters of the measured data, and the simulated data was matched to this. So in the simulation it was the same resolution used, the same bandwidth was used in the resolution, in the simulation.
Okay, thank you, Simon. Yeah, here's a very long text. I don't know if it's really a question, but I will read it down. I'm wondering about the use case as formulated on slide 3. Recognition identification can be done in various ways. One way is IFF, but that seems problematic for civilian airliners. So they have a transponder that can be used in an identification attempt, and that may be easier than interpreting an image. On the interpretation of image, one may have a look at people with airliner spotting as a hobby. Oh, yes, now I understand. Yeah, then go ahead. What do you say about transponders and identification?
Yes, in the end, that's correct. The IFF system is a good example, actually. So, so if you want to identify a target, I mean, the standard way for air traffic control, for example, is the IFF system of an aircraft. There's one also famous example that was I think it's also Malaysian Airlines, that was, where the pilot actually switched off the IFF on purpose to actually crash, and he crashed the aircraft into the, I think, Indian Ocean. And there was a long time searching already in the wrong direction, actually. They were searching, I think, more to the north in the direction of Vietnam, I think, or something like this. And it's not confirmed, but I know that there was a detection on an military radar, actually. I don't know the country. I think maybe it was Vietnam or Cambodia. I don't know, actually. And they still don't know if they really detected this target, this aircraft. I mean, that's the point where we can see where the IFF was not working. And yeah, it's could be a solution if this military radar would be able to have this ATR capability to identify it as an airliner. If we don't talk about civil airliners, we talk about military aircraft. So in this case, the IFF system is, of course, also switched off, or maybe also manipulated on purpose or something like this. There's also a quite high need for a classification system that works quite well, that we identify these aircrafts.
Once you have an object and track, you may have an easier go on ISAR. Are you considering such aspects?
Yes, so the track is actually necessary to perform an ISAR because we need some motion compensation. So without tracking, there's in the end no ISAR imaging, or let's say not a really useful one, let's say, because we have a certain motion of the aircraft, and we need to compensate for this. And if you just measure and want to just apply some, I mean, you can apply some autofocusing methods. But at least our experience is, as we have the motion of the aircraft, we get a better results if you first compensate for this and then run the autofocus algorithm. So we already help the autofocus a bit. So we need the tracking first. That's also information that we have. We created a track, use this information to do the so-called range compensation in ISAR imaging. And then, we actually run the autofocusing and produce the ISAR image. So I hope that answers the question. I hope that became clear a bit what I mean. So if we use the tracking, that's the main part actually, the main information.
Good, Simon. The next question, how many hyperparameter did you use in the algorithm?
That's a good question. Actually, I don't know. It's not much. It was the smallest threshold, so the thresholding itself and the number of thresholding. That's the number of iterations. These are the main parameters. The other one is the way how to decrease the threshold. So we have I used mostly the exponential decrease. So I have a maximum value, a smallest value, and then at the beginning I have quite large steps to increase the number or decrease the threshold. The other option would be linearly to decrease it. That's also something I tried, but mostly I got better results with the exponential one, because at the beginning, if we have this high correlations, we get some good results already if we have some big steps at the beginning, and later if we have this higher competition between waveguides and point scattering, we use smaller steps because we have more closely related targets, let's say. These are actually the algorithms already of the thresholding, and then of the waveguide model, it's the in the end, it's only the opening and the length of the waveguide. So the opening defines for circular waveguides the so-called mode, so just the radius, and the length of the jet engine for the classification or for the propagation length. I think that's it. These were the parameters in the algorithms I used.
That's all the questions for today. Thank you again for your participation and all the questions. I hope you enjoyed it. Again, you'll get a short survey tomorrow. We would appreciate if you take the 2 minutes and answer the 4 questions. On Friday, you will receive the presentation slides from today. And if you want to share the presentation with your colleagues or friends, today in 3 weeks it will be published on our YouTube channel Fraunhofer FHR. That was the first Radar in Action session in 2020. The next dates are not fixed yet. I assume that we will continue in May, however. As usual, we will inform you early by email on our website or via social media. Take care, stay healthy. See you soon.